Welcome to a lesson with Dr. Powell. We're going to look at the acceleration vector function that's associated with a position vector function of a path or a curve in 3 dimensions. Now we're going to write this in terms of a tangential component and a component that's a normal component, meaning we're going to rewrite A as some scalar multiple of the unit tangent vector plus some scalar multiple of the unit normal vector. So if we have a curve, this is the unit tangent vector, it's unit normal vector, and we're wondering, what is the acceleration in this direction? And then what's the acceleration in that direction? Now, if we figure out the acceleration in this direction and the acceleration in that direction, rescale t and n accordingly, and add them together, we'll actually end up getting the acceleration vector itself. So we're going to split up the acceleration vector into a tangential component and a normal component. So let's first give some motivation for how this works. First, let's get our position vector, and then we take a derivative of this to get the velocity vector, just with respect to t. Just take a derivative, straight derivative, component-wise, and you get the velocity vector. Now, the velocity vector itself is actually in the direction, it's tangent to the curve itself, it's actually in the direction of the unit tangent vector. But if we were to multiply the unit tangent vector by the length of v itself, this is actually the same thing, because t is the direction of v, and then this is just the length of v. So then multiplied together, of course, will be v. Now, another way of notating the length of v is simply ds dt, where s is the arc length, or the length of the curve as we go along. So the derivative of the position or the distance traveled along the curve is equal to the length of the velocity vector. So we could rewrite v of t as a scalar. This is just a scalar product, so just a number or a length rescaling this vector times the unit tangent vector. So if we want to move now from velocity, let's think of this as velocity, and we'll take this and we'll move from there to acceleration. And we do that by taking a derivative. Now we could do that by just taking components here and taking the derivative of those to get here. That's great, but we're going to do it another way right now, just for motivation's sake, to see how we get the different components with t and n popping up. So let's just take the derivative of this right here, this product. Of course, it's a scalar times a vector, but still the product rule holds in this case very nicely. So proceeding, we take the derivative of, and I'm going to rewrite this ds dt simply as s prime. Okay, s prime. So we have s prime t, and I'll just write s prime t here for this. And to take its derivative using the product rule, I'm going to have s double prime t plus s prime t prime, just using the product rule straight. Now, this looks good. This looks like something times the tangent vector. And remember that since we've taken a derivative, what I've just written here is actually the acceleration. This whole thing right here is a, or the acceleration vector function. So so this looks good, but let's look at this part right here. Now this is t prime, and you remember that if we take t prime and you divide it by the absolute value of, you divide it by the absolute value of t prime, you end up getting n itself. So I'm just going to go here and multiply by the absolute value of t prime right here, s prime, so that these would cancel. So this is actually equal to what I have here. But the reason why I did that is because I see an n popping up right here. So you have an n, and then I have an s prime, and then the absolute value of t prime. Now I'm going to throw something else in here. If I take the absolute value of t prime and I divide it by the absolute value of v itself, let's see what that is. Now, remember what this is. This is the same thing as writing dt all over ds dt, where this is the same as this, and this is the same as this, and we're taking the length of that, right? And so that's actually equal to the length of dt ds, which is precisely the curvature. That's going to be pretty handy. Then, but I can't just replace t prime by this. I have to multiply by the absolute value of v. I get that. And notice that I get two things canceling here. Or sorry, what I end up getting is I end up getting this, right? Those cancel if I want to work back to get this, but this right here is just the curvature. So I can replace this from that calculation. So I can replace this by kappa. And then you see this absolute value of v. That's the exact same thing as the derivative of the arc length, which is s. So really this is just s prime. So this is like s prime times s prime. So it's just s prime quantity squared. So what we end up getting is that the acceleration itself is equal to s double prime t, as we had before, plus, and then we have s prime squared kappa n. So this is the component in the n direction. This is the component in the t direction. Now, for computation's sake, maybe there's a nicer way of actually working this out. Well, for one, if we can just find s double prime, that's a lot easier. Then after we find s double prime, we think since t and n are perpendicular to each other, we'll use this notation for perpendicular to each other. That means we can use a Pythagorean theorem type idea to find, to figure out what this component should be. Because if we have A and it has a given length, suppose that's the length of A, and let's suppose the tangent in the tangent direction, we have a certain length, it's s double prime. And maybe we can even notate this as AT, the length in this direction, which is the same as this. And how do you find this? Just use the Pythagorean theorem, and it's a little easier. So you just do that minus and then AT squared. So that's kind of the idea of how we're actually going to compute that. And just remember that s double prime, the way we get that is first we compute s prime, which is just the absolute value of v. And then we just take that and we take the derivative of that with respect to t. So it's really the absolute value of v prime is equal to the tangential component. So this is really all you need to remember. Compute the absolute value or the length of v and take the derivative of it, and that is the tangential component. To get the other component, just use the Pythagorean theorem. We'll see an example of this in the next video. Thanks for watching.